Hey physics babies, welcome to Pandemic Education. Today this is episode 7 and we are just going to be reviewing all of your questions from Unit 5 lessons 1, 2, 2.5, and 3. I'm just going to be using the document camera and we're going to work through all those problems, so let's get into it. Okay, so we're going to start with Unit 5 lesson 1. I don't expect you to copy down every single problem, but I do want you to show the work like I am. So that means we are showing our givens, we are writing down the formulas, we are plugging in numbers, and then we are writing down our final solution. So the first problem, a negative charge of negative 2 times 10 to the negative 4th coulombs and a positive charge of 8.0 times 10 to the negative 4 coulombs are separated by 0.60 meters. What is the force between the two charges? So let's start off. I'm given that I've got one charge, Q1, that's equal to negative 2 times 10 to the negative 4 coulombs. I've got another charge, Q2, of 8.0 times 10 to the negative 4 coulombs. And I've got a distance between them of 0.60 meters. And I want to know what the force is between the two charges. So I want Fe. So, I am going to use my handy-dandy formula sheet. If you haven't made one, you definitely should. That's got all of the formulas we've talked about so far this unit. I would recommend a formula sheet because, I'm not there to write them all down for you on the whiteboard. So, make yourself a formula sheet. Super handy. An index card will work just fine. So, based on what I'm given, I know I'm going to use this formula right here, where we've got Fe equals K times Q1 times Q2 over my distance between them squared. And I know K is a constant, that is 8.99 times 10 to the 9th Newton meters squared over coulombs squared. So I'm going to use this formula and this value. We're going to plug in what we know. We've got Fe equals 8.99 times 10 to the 9th times negative 2.0 times 10 to the negative 4 times 8.0 times 10 to the negative 4. And that's being divided by 0.60 squared. Once you have it written down, you can go to your calculator. And we've got 8.99 times 10 to the 9th times negative 2.0 times 10 to the negative 4th times 8.0 times 10 to the negative 4. Double check that I typed that all in right before I keep going. Okay, divided by 0.60 squared. I'm getting negative 3995.55555. So let's write this down. Equals negative 3995.5. We're going to go 3 sig figs. So I look at my 1, 2, 3, the 4th number. It is a 5, so that means I'm going to take this number and round it up. When I round this 9 up, that means it's going to be a 10. I have to round this 9 up. It's going to be a 10. It's going to be a 4 here. Do not forget to include these zeros. So I'm going to get that Fe equals 4,000 newtons. I started off with 3,995. Do not drop this down to be 400 and say you've got 3 sig figs, okay? If I've got 4 placeholders here, I need to have 4 placeholders here. It's okay if they're a 0. Remember, zeros don't count as sig figs. The last thing I want to talk about is the sign on this. I got a negative number, but we need to go back to the beginning of our problem and think about it. If I have a negative charge and a positive charge, are those two charges attractive or are they repulsive? Opposites attract, so this is going to be a positive force because they are attracted to each other. Okay, so remember, negative 4 Fe equals repulsive, and then a positive Fe equals attractive. You need to go back every time that you do a problem like this and think about it. to decide whether this force should be a positive force or a negative force. The answer that the problem gives you will not be correct. Okay? All right, so moving on, problems like this from our exit tickets, if you didn't include the correct units, you got this problem wrong. Make sure you include units at the end of all of your answers. All right, this problem is very similar. We've got a negative charge, so I'm going to start writing down my givens. Q1 is negative 2.0 times 10 to the negative 4 coulombs. We've got a positive charge, Q2, of 8.0 times 10 to the negative 4 coulombs, and they're separated by 0.30 meters. And again, we want the magnitude of the force between them, and we want to know if it's repulsive or attractive. So we want Fe. I'm going to use the same formula that we used in the first problem. Fe equals K Q1 Q2 over D squared. Let's plug in what we know. Fe equals 8.99 times 10 to the 9th, because remember K is a constant, it's always 8.99 times 10 to the 9th, times negative 2.0 times 10 to the negative 4, times 8.0 times 10 to the negative 4, all divided by 0.30 squared. Getting out our calculator, can start typing 8.99 times 10 to the 9th times negative 2.0 times 10 to the negative 4 times 8.0 times 10 to the negative 4 divided by 0.30 squared. And I'm getting 15982. Double checking that I typed all that in correctly. Okay, so I'm getting that Fe equals negative 15982. We are going to look at our, we got 3 sig figs, 1, 2, 3. We look at that fourth number. It's an 8. So I know this 2, I'm going to drop down and make it a 0. This 8, I'm going to turn it into a 0 and round the next number up. So this 9 will become a 10, which means this 5 needs to become a 6. Our units are newtons, and we need to decide, is this going to be an attractive force or a repulsive force? If I've got a negative charge and a positive charge, the forces are attractive to each other, so I'm going to make it a positive here. I'm just going to circle this number, because, you know, why not? And put a box around my final answer. All right. That is it for lesson 1. I lied. I flipped the page. I forgot there's one more problem from lesson 1 that I want to talk about. So, I gave you this charge table, and I'm asking you to find the charge between A and C. So let's start with our givens. Charge A, we'll call Q1, and we'll call charge C Q2. So charge A, the Q on it is 0.002, and it's a positive. Charge C, Q2, equals negative 0.002 coulombs. I want the force between them. So looking at my formula sheet, I know K, Q1, Q2. If I know their distance, I can solve for this force. So looking over here at their locations, Q1 is at 0. So if I were to draw a little picture, right, and here's like my little graph, charge 1 is right here at 0 meters. Charge 2 is then at 2 meters. So I've got charge 2 all the way over here at 2. 1, 2, and then, like, you know, this would keep going, so 3 would be over here. So the distance between Q1 and Q2 is exactly 2 meters. So I know my distance here is 2.00 meters. Now that we know this distance, we can again use that same formula, Fe equals K, Q1, Q2 over D squared. Plugging in what we know. Times 0.002 times negative 0.002, all divided by 2.00 squared. Whew, that's a lot of zeros. So 8.99 times 10 to the ninth times 0.002 times negative 0.002 divided by 2.00 squared. I'm getting 8990. So let's see. I'll look at the first three. 1, 2, 3. Look at that fourth number. It's a 0, so I'm just going to leave it alone. So Fe equals 8990 newtons. We need to decide, is this going to be positive or negative? My calculator told me it was a negative, but if one charge is positive and the other is negative, are they attracted to each other or do they repel each other? They attract each other, so my force is going to be a positive force in between them. Alright, now that's it for lesson 1. Moving on to lesson 2, where we started talking about electric field. Question number 1 asks, what is the electric field at a position that is 1.6 meters east of a point charge of positive 7.2 times 10 to the negative 6 coulombs? So I've got a Q of 7.2 times 10 to the negative 6 coulombs. I've got a distance, D, is 1.6 meters. I'm going to draw myself a little picture. So I've got my charge right here, my Q. And I want to know 1.6 meters east of this charge. So north, south, east is this way, and then west is over here. I am right here, and my distance equals 1.6 meters. This is a positive charge. Let's look at our formulas. I know that I can use this equation, that my electric field is equal to K times Q, the charge, divided by the distance squared. So let's do that. E equals K times Q over D squared. Plugging in what we know, K still is 8.99 times 10 to the ninth times the charge of my particle, 7.2 times 10 to the negative 6 divided by 1.6 squared. Handy dandy calculator. 8.99 times 10 to the ninth times 7.2 times 10 to the negative 6 divided by 1.6 squared. Whew, that's a big old number. Look, we're getting that the electric field is 25284. That's more than 3 numbers, so I'm not even going to worry about writing the decimal. We measure electric field in newtons per coulomb. So let's look. 3 sig figs. 1, 2, 3. We look at this fourth number. It's an 8, so I'm going to drop everything after it and make it a 0. This 8, I'm going to round up and make this 2 a 3. So I'm getting that my electric field is 25300 newtons per coulomb. The last thing we need to think about is the direction the electric field is pointing. So, if I have a positive charge, what direction does the electric field point? Towards the charge or away from the charge? It points away from the charge. So, you could have said to the east, because it's moving away from the charge, right? You could have said to the right, because that's the direction. Or you could have just said away from charge. Any of those would have been fine, but it's important when we have electric field that we talk about both our units as well as thinking about the direction that it's pointing. You do not need all 3 of these, Just one would have been more than enough. Okay, moving on. Okay, the next problem we're going to do, the electric field that is 0.25 meters from a small sphere is 450 newtons per coulomb towards the sphere. And we want to know what the net charge is on the sphere. So let's see, my givens are this, D equals 0.25 meters. I've got an electric field of 450 newtons per coulomb towards the sphere. And I want to know the Q on the sphere. So, again, let's look at our formula sheet. We can either think about how the electric field is equal to the force divided by the charge, or is equal to KQ over D squared. Based on the fact that I know a distance, I'm going to go for this equation right here. So, I'm going to write that E equals KQ over D squared. Let's plug in what we know. E is 450. K is 8.99 times 10 to the 9th. We don't know what Q is, so times Q. And we're dividing that by 0.25 squared. Now we need to start doing some inverse operations to get Q all by itself. The first thing we're going to do, I see division, so I need to multiply to get rid of this before I can do anything else. So I'm actually just going to multiply by 0.25 squared on both sides. You can find 0.25 squared and then multiply by that number, but it really doesn't matter. Both are perfectly fine options. You do whatever you like best. So I'm going to say 450 times 0.25 squared. And I'm getting this 28.125 equals 8.99 times 10 to the 9th times Q. Now to get Q alone, I'm going to divide both sides by 8.99 times 10 to the 9th. In my calculator, I'm going to leave this number up and literally just type divided by 8.99 times 10. Oh no. Here we go. Times 10 to the 9th. And I'm getting 3.128 times 10 to the negative 9. That's what this calculator is telling me when we get this E in an answer. So I'm going to write it over here. Q equals 3.1284 times 10 to the negative 9. We use coulombs to measure charge. We need to do two things right now. We need to decide if this is a positive charge or a negative charge, and we need to round it to 3 sig figs. So 1, 2, 3, we look at this fourth number. Anything after that, I'm going to drop and turn into zeros, not just completely get rid of. This 8 is going to make this 2 round up, so I'm going to say that my charge is 3.13. If it's after the decimal, I'm actually not going to make them zeros. I'm literally just going to get rid of them. Little sig fig review. Coulombs times 10 to the negative 9 coulombs. So now, if the electric field at the beginning is pointing towards this charge, towards this sphere, is my final charge positive or negative? It's going to be negative. Remember, electric fields always point from positive towards negative. So if the electric field is pointing towards something, that means the charge on it has to be a negative charge. Okay, I hope that helped. We're going to move on to Unit 5, Lesson 3, where we started talking about electric potential difference or voltage. First problem, a uniform electric field is established by connecting the plates of a parallel plate capacitor to a 12-volt battery. I'm going to start writing down things that I know. I know that volts is electric potential difference, so I know delta V equals 12 volts. A charge, Q, of 6.24, oh my god, too aggressive, you guys. 6.24 times 10 to the negative 6 coulombs moves from the negative plate to the positive plate. We want to find the amount of work done on the charge. So, I know we haven't really talked about what a parallel plate capacitor is. We'll talk more about them as we kind of get deeper into this unit. For now, what you need to know is that there's a positive plate, there's a negative plate, and then there's an electric field running between them. Okay? So, looking at my formulas for voltage, for electric potential difference or volts, I wrote down 3 different formulas from that lesson. Looking at what I'm given and what I want, I'm going to use this first formula. So, my delta V equals the work done divided by the charge. So plugging in what we know, 12 equals the work done divided by 6.24 times 10 to the negative 6. Moving to my calculator, 12 times 6.24 times 10 to the negative 6. I am getting that the work done equals 7.488 times 10 to the negative 5. Let's turn this into 3 sig figs. 1, 2, 3. Let's look at this fourth number. It's after a decimal point, so I'm going to end up dropping it entirely. But before I do so, it's going to round this number ahead of it up 1. So I'm getting that the work done equals 7.49 times 10 to the negative 5. What do we measure work in? We measure work in joules. It should be a refresher from our last unit. Once you've got units on here, you are good to go. Next problem. So this next problem was a little long, so I didn't want to write it all out, so instead I just looked at the typed version. We're going to read it, and we're just going to pick and choose the important stuff. A parallel plate capacitor is a device that, when hooked up to a battery, can store electrical energy between its 2 metal plates by separating charge so that one plate is more positively charged than the other. This creates an electric field between the plates. Air separates the 2 metal plates as they charge, and since air is a good insulator, it keeps the plates from just discharging until it is necessary to do so. When a capacitor releases the electrical energy that has been stored, it usually does so very quickly. An example of this is the flash on a camera. The flash is a capacitor that charges when it is not in use and then releases all of its electrical energy in a split second when taking a picture. This allows for such an intense flash of light to occur. That was a lot of information, but do we need it? Did it even ask a question in there? No. So let's move on. Let's say that a parallel plate capacitor has plates that are separated by 0.75 millimeters. So I've got one plate, and another plate, and between them is a distance d. The distance is equal to 0.75 millimeters. Okay. The electrical field between the plates has a magnitude, so E has to equal 1.2 times 10 to the 5 volts per meter. We want to know the potential difference between the plates. So I want to know delta V. Thinking about my formulas, hey, wait, volts, delta V is equal to the electric field times the distance between the 2 plates, or the distance between 2 objects. So I'm going to use that formula. V equals E times D. Now, before we do anything crazy like start plugging numbers in, we need to take this 0.75 millimeters and turn it into meters. Remember, we use standard units, we use meters, we don't use millimeters or centimeters. So, let's go. King Henry died by drinking chocolate milk. We are sitting at millimeters, and we want to move to our base unit of meters. So I'm going to take my decimal point and move it 1, 2, 3 spaces. So we've got 0.75, and I'm taking my decimal movement 1, 2, 3. My distance is equal to 0.00075 meters. All right, now that I know that, I can plug it in. Delta V equals 1.2 times 10 to the 5 times 0.00075. Sorry guys, I know it keeps going in and out of focus. I hope I'm catching it often enough. 1.2 times 10 to the 5 times 0.00075. I'm getting 90. Hey look, this question that was from your independent practice also said we should get 90. Perfect. Delta V equals 90 volts. So remember, regular V is volts, delta V is the electrical potential difference. Make sure you include that delta. I tend to forget it. Don't be like Miss Pop. Moving on. We've got 3 more questions and then we'll be done. Okay. The gap between electrodes in a spark plug is 0.060 centimeters. This is really hard to see, but it's centimeters. So my distance is 0.060 centimeters. Producing an electric spark in a gasoline air mixture requires an electric field, E, has to equal 3.0 times 10 to the 6th volts per meter. We want to know the minimum potential difference, that's a nice way of saying delta V, must be supplied by the ignition circuit to start a car. In case you weren't sure, spark plugs, they're in your engine. They run, they create the spark that ignites the fuel and lets your car run. So, we want the delta V. I'm going to use that same formula that we just looked at, which said delta V equals E times D. Again, though, my distance has to be measured in meters. So the first thing we need to do is turn centimeters into meters. King Henry died by drinking chocolate milk. I'm sitting at centimeters. I want to go to my base unit of meters. I'm going to move my decimal place 1, 2 to the left. 0.060. We're going to go 1, 2. And I get that my distance is 0.0006 meters. Now that we know that, delta V equals 3.0 times 10 to the 6th times 0.0006. To the calculadora, 3.0 times 10 to the 6th times 0.0006. And we get 1800. 1800. What are the units on this? Volts. And there we go. Almost there. All right. 2 charged parallel plates are 2.0 centimeters apart. D equals 2.0 cm. The magnitude of the electric field between the plates, E, is 1800 newtons per coulomb. We want to know the electric potential difference between the fields. I want, again, delta V. So we're going to use the same formula. Delta V equals E times D. We need to take our distance and turn it into centimeters. King Henry died by drinking chocolate milk. Oops. I'm sitting at centimeters. I want to go to meters, so I'm going to move my decimal place 1, 2 to the left. 2.0 is going to become 1, 2. 0.02 meters. Now that we know that, let's plug it in. Delta V equals 1800 times 0.02 meters. I'm not going to put the meters there, I'm sorry. Using our lovely calculator, we're going to say 1800 times 0.02 is 36. And the units on that, again, are going to be volts. All right, so from the plates above, so we're still using all of this information, how much work is required to move a proton charge of 1.6 times 10 to the negative 19 coulombs from one plate to another? Well, let's see. Looking at my formula sheet, I know distance, I know the electric field, I now know the electric potential difference, and I know the charge. I want work. Let's use this formula right here. It's got work, it's got charge, it's got electric potential difference. Delta V equals W over Q naught. So my delta V, which was 36, equals the work done divided by 1.6 times 10 to the negative 19. To get work all by itself, I'll multiply both sides by 1.6 times 10 to the negative 19. So we're going to do 36 times 1.6 times 10 to the negative 19. And we get 5.76 times 10 to the negative 18. Remember, the units on work are joules. All right, so that's going to be it for our Unit 5 review of Lessons 1 through 3. If you have any questions or concerns, if there's anything that you want me to go over, if you want to ask me anything, please come to office hours. My office hours are Monday through Friday from 2 to 3 o'clock. Stop by, ask a question, go see another teacher, say hey, whatever you need to do. That's it. With this review, there is a short quiz that's on Google Classroom that I want you to complete by Saturday at midnight. Do great things, and I love you lots. Bye.